remember we were actually discussing the situation where I have a potential well and a particle is confined to the potential well. And it is taken to be, the potential well is taken to be located between minus a and plus a, and in that region it has a depth of minus V0, and the origin is taken to be at this point, which is x is equal to 0. And as I told you yesterday, what happens is that if the system obeyed classical mechanics, the particle can be trapped inside the potential well, and it can in principle have any energy from minus V0 to 0, and if its energy is greater than 0, then it will not be trapped, but it will go away. That is how the system was. And then we wrote down the wave function for the system in the 3 regions, this region, the second region, as well as the third region, region 1, region 2, region 3. And in this region we wrote the wave function as b1 e to the power of kappa x. These are things that we have already done. No, I think it was a1. Here it was written as b1 cos kx, while on the other side it was written as a1 c1 e to the power of minus kappa x. Well, actually strictly speaking, I should say that it is b1 cos kx plus b2 sin kx but then we said that okay, because the potential is symmetric, the wave functions may be symmetric or antisymmetric. That means, if I change the sign of x, the wave function may remain unchanged, or it may at the most change sign, and we decided that we will look at only, at least at first we will look at solutions which are symmetric, and therefore we had removed this b2 sin kx. That will be included when we analyze the wave functions which are antisymmetric. So, then we also said that the wave functions have to be continuous, a wave function has to be continuous everywhere, and not only that, the derivative of the wave function also has to be continuous. Now, at this point I would introduce a little bit of mathematics which may not be familiar to you, but this is really beautiful mathematics, and that concerns the subject of Dirac delta function. Now, I am sure you would be familiar with a function like e to the power of minus x square. Okay. A plot of e to the power of minus x square against x, how would it look like? Actually, it is very easy to visualize it. It is what is referred to as a Gaussian, and the way it behaves is this. At x is equal to 0, it has its maximum value, and then as x increases either in the positive direction or decreases in the negative direction, then what will happen? The value of the function simply goes on decreasing. And if I wanted to calculate the area under this curve, what will you do? Well, this area, if I wanted to calculate, you will have to integrate this object from minus infinity to plus infinity. This is a standard integral, a difficult integral actually, but the answer is known, and what happens is that the answer is actually square root of y. Okay. This is a very well known integral, it can be evaluated, and therefore, if I had thought of instead of e to the power of minus x square, I suppose I had thought of e to the power of minus x square by square root of pi. Okay. What will happen is that this function, if I plotted instead of e to the power of minus x square, if I plotted that function, of what is going to happen is that the height of the function will look exactly the same, but the actual area under the function would be how much? It will be equal to unity. Okay. So, let me imagine this is this plot itself is in such a fashion that I am plotting e to the power of minus x square by root pi. So, that this entire area, let me now say it is equal to 1, the total area. Okay. And now suppose I say, okay, I am going to modify this function a little bit. What I want to do is I want to say, okay, e to the power of minus a x square, right, and I am going to multiply it by, well, if I multiply this by 1 by square root of pi, the area under the curve will not be unity, but if I multiplied it by square root of a by pi, then what will happen is that the area under the curve will still be unity. So, you can easily show that. That means, if you integrated this, answer is going to be 1. So, suppose I now say, okay, I have this function square root of a by pi into e to the power of minus a x square. If a is equal to 1, it would have this appearance. Okay, it would have this appearance, but suppose a is equal to 5, what would be the appearance of the function? If a is equal to 5, you can see two things happening. One, first of all, you will have a square root of a there. So, if you put a is equal to 5, this is getting multiplied by square root of 5, correct. That means, the value of the function at the origin actually has increased by square root of 5 at the origin. At the origin, you see x is 0. So, therefore, what has happened is that the height of the function at the origin has increased, but the area under the curve is still 1, and that obviously means that the width of this function has decreased, right. So, if you think of a being 5, what would happen is that you would get another curve which would look like this. Its width has decreased, but its height has increased in such a fashion that the area under the curve still is equal to unity. So, suppose I increase the value of a further 5 to maybe 25, what would happen? The function will become very narrow, but its height will be very large. Still the area under the curve will be unity, it will be the same, the area is not going to change. So, what I want to do is I imagine that this a becomes infinitely large, then what will happen? The function will have infinite height at the origin, and its width will be extremely small. So, it will be just a spike, okay. And that function is the one that is referred to as the Dirac delta function. So, how will I define Dirac delta function? I will say delta of x is equal to limit, I have to take the limit where a, this number a approaches what value? It has to approach the value infinity. So, this is my definition of the Dirac delta function, and the way I have defined it, you would realize that this is a function which has an infinite value at the origin, and anywhere else what is the value of the function, because it is such a narrow spike, anywhere else even close to 0. If you have a point close to 0, but not 0, then what will happen? The function will be having a negligible or a small or a value which is very small, in fact 0. Right. So, another way of defining the same function is to say that okay, delta x is equal to infinity if x is equal to 0, and if x is not equal to 0, what will happen? Even at points very close to x is equal to 0, what would happen is that the function is extremely narrow, because I am taking the limit here tending to infinity. So, what will happen is that if x is not equal to 0, the function will actually have the value 0. Okay. So, that is another way of defining the function, but not only that, you can also notice that integral of delta x dx from minus infinity to plus infinity must be equal to, it has to be equal to unity. The area under this curve is always unity irrespective of what the value of a is. Even if a is extremely large, the area is still equal to unity. So, therefore, this has to be obeyed. So, this is a rather peculiar function. I mean, when you think about it physically, there is nothing to this function actually. It has a value only at one particular point, and that is infinitely large. Everywhere else the function is 0. But this is a mathematically a peculiar function, because this definitely is not a continuous function, as you can see, because as you go along the x axis, what happens, its value is everywhere 0 until you hit the point x is equal to 0, and at that point it has an infinite value, and then when you pass that point, the value of the function is again back to 0. Okay. But now suppose I say okay, I am going to take this function and I am going to integrate it. Let us say I take the function delta, I will denote the variable of integration as x1, I am going to multiply it by dx1 and integrate. From minus infinity to plus infinity, I can integrate. I know what the answer is going to be. The answer will be unity. But suppose I now say okay, I am not going to integrate up to plus infinity, but I am going to integrate only up to a variable value which I denote as x, suppose. So, that means you see I have this very narrow, very peaked function, that is my function. To represent it physically, this is my function, it is located at x is at 0, it is located at 0, and what you are doing is you are doing an integration from minus infinity up to this particular point, up to that point, let us say. What will be the answer? Everywhere, you see, everywhere in the range of integration the function is 0, so the integral will also be 0. Correct. So, up to even if you are very close to 0, even if this x is very close to 0, what will happen? The answer will still be 0. But suppose x was on the other side of 0, right? Suppose x was here, just on the other side of the peak, what will happen is that the answer will be equal to unity, right. Now, the function will be 0, but the integral, because when you are integrating you are actually calculating the area. See, if you have integrated up to this point, the area, total area of under the curve from minus infinity up to there is actually 0, but once you have integrated up to this point, you see that actually encompasses this peak, and because the peak is there, the area of the peak is unity. So, the moment you say that your x is on the other side of 0, the function will the integral will have the value unity. So, therefore, you can say that this is a function. Okay, let me call this function theta of x. What is special about this function? Theta of x is a function such that if x is less than 0, what is its value? It is 0. And if x is greater than 0, what is its value? It is 1, correct? It is unity. And the way we have been defining it, actually, if you like, you can ask, I mean, what is the value of the function when x is equal to 0 itself? We will take a very simple attitude. You see, you think of this as a peak. The peak is symmetric about the origin, about x is equal to 0. So, if you are integrating up to x is equal to 0, what will happen? You would have covered half of the peaked function, and therefore, you will say, okay, if x is equal to 0, then it will have the value half. It is the simplest way in which I can think of this function. And if you made a plot of this function theta of x, what is the appearance that you are going to get? If you made a plot of theta of x, what would be the appearance? Well, it is a simple thing. What happens is that up to x is equal to 0, the value of the function is 0. So, the plot will coincide with the horizontal axis up to this point, and at that point itself, with our analysis tells me that its value is half. So, it is somewhere here, and beyond that, when x is greater than 0, what happens? The function is 1. Thank you. Thank you. When x is equal to 0, it is equal to half. Okay. So, therefore, beyond this point, what will happen is that the value of the function is actually equal to unity. Right. Now, if you look at this, actually, I mean, if you like, you can draw the function something like this. And when you look at this, I mean, you see what is happening is that if you are moving along this direction, up to here the function has the value 0, suddenly the function jumps, it goes up by 1 unit. It is like a step, and therefore, this is referred to as the step function. In fact, the height of the step is unity. So, this is referred to as unit step function. You can think of step functions which have different heights if you want. All that you need to do is you just multiply this by, let us say 4, you take this function, multiply it by 4, then the height of the step will be equal to 4. And this was originally introduced by Heaviside. I think the name has an A in it, I am not completely sure. Heaviside unit step function. So, you look at this, you see, why did I introduce this function at this point? The answer is that here I have a Dirac delta function which is which has the value infinity. It is a very strange function, its value in this range is 0, its value in that range is 0, at that point alone it has an infinite value, a very ill behaved function. But you look at the integral of that function, it is a step function and it is a discontinuous function. You can see that this function changes discontinuously, right. I can make the argument in the reverse. If I had a discontinuous function, what will happen to the derivative? The derivative would be a Dirac delta function, right. If I have a discontinuity in a function, its derivative at that point will be a discontinuous function, sorry, will be a Dirac delta function. Okay. Now, suppose I think of another function. This is the last function that I shall discuss as far as the mathematics is concerned. Suppose you think of this particular function, magnitude of x. So, how will a plot of magnitude of x against x look like? It is a simple thing. If x is greater than 0, magnitude of x is x itself. So, if you made a plot, this is the kind of appearance that you are going to get, right. X, magnitude of x plotted against x would be just a straight line like this, but if x is negative, what will happen? The plot will be actually somewhat similar, it will be looking like that, right. Magnitude of x, if you plot against x, for negative values of x, this is the appearance. So, suppose I think of d magnitude of x by dx. Well, again you can take the simple physical interpretation. It is, what is the derivative? It is the slope. And what about the slope of this curve that, or this two straight lines that I have drawn? You see, when x is greater than 0, the slope is actually how much? How much will be the slope? Slope is 1, right. So, therefore, if x is greater than 0, this is actually 1, and if x is less than 0, what is the value of the function? Again you look at the straight line, you see, if you look at this straight line, you would realize that this has a negative slope. In fact, the slope is minus 1, this slope is minus 1. So, therefore, what happens is that if x is less than 0, the answer is going to be equal to minus 1. Okay. So, what is this this derivative? This derivative is an interesting function which has the value plus 1 if x is greater than 0, while it has the value minus 1 if x is less than 0. So, if I made a plot of this function, this new function, okay, how will it look like? Let me continue here. X along the horizontal axis and the derivative of magnitude of x with respect to x is plotted along the vertical axis. And obviously, what happens is that if x is less than 0, the answer is minus 1, that is the plot, and if x is equal to plus 1, sorry, if x is positive, what will happen? The value has, the function has the value plus 1. So, at x is equal to 0 itself, what has happened? The function has discontinuity, correct. So, if you wanted to make a plot of the function, you will say, okay, it goes like this. At x is equal to 0 itself, it jumps, it has a discontinuity, and the size of this discontinuity is how much? The height of the discontinuity, it is equal to 2 units. Okay. And so, if I had differentiated this function further, what would have happened? Suppose I want to take the derivative of that function. Well, the function is a constant in this region, so there the derivative is 0. Function is a constant in that region, there again the derivative is 0. But at this point itself there is a jump discontinuity of 2 units. So, therefore, the derivative of the function will actually be 2 times. Remember what happened with the delta function. If there was a delta function, then there is a discontinuity of 1 unit in the function, in the integral, correct. So, if this function has a discontinuity of 2 units, its derivative is going to be 2 times the Dirac delta function, correct. That is what happens. Now, let me again tell you the reason why I introduced this function, because you look at this function, this is the derivative of a function which is shown here. You see that the derivative of the function is discontinuous, but the function itself, the function is this, the function itself is continuous, correct. So, let me summarize everything that I have told you. If the derivative is a delta function, then the function will have discontinuity, right. If the derivative is a delta function, then the function will have a discontinuity. If the derivative is discontinuous, then the function itself will be continuous. So, this is what we were using in the previous lecture. Where did we use it? We said that we have the Schrodinger equation, we said that we have the Schrodinger equation which may be written as what was the equation, d square psi by dx square is equal to I mean the only way I can remember this is to write the equation the way I remember and then rearrange. That is the equation. So, if I rearrange that, what will I get for d square psi by dx square? This is the equation that I will get, right. And the way the potential energy is in this problem, what has happened is that the potential energy has a discontinuity. That simply implies that the second derivative has a discontinuity, but even if the second derivative has a discontinuity, the first derivative is guaranteed to be continuous. And not only the first derivative, naturally if the first derivative is continuous, then the function itself will be continuous. So, therefore, the fact that the wave function has to be a continuous function of position can be derived from the fact that the wave function obeys the Schrodinger equation. Okay. The fact that let me repeat, the fact that the wave function is a continuous function can be derived simply from the fact that the wave function obeys the Schrodinger equation. And if the potential is not peculiar, right, if it has only a finite discontinuity, then even the first derivative of the wave function will also be continuous, right. Unless your potential is very peculiar, even the first derivative will be continuous. That is what we used in the last day's lecture. So, let us now do that, or let me just remind you what happened with this particular function. We impose the condition that the wave function at this point should be continuous, and we also impose the condition that its derivative must also be continuous, and we arrived at an equation. Now, strictly speaking, what I should do is I should impose the same condition at the other side, at the other end also. So, let me just do that today, right. Just let me just impose the condition that the wave function should be continuous at this point, which is x is equal to a. So, the wave function on the left hand side is given by this function, while the wave function on the right hand side is given by that function. Okay. So, how will you impose the condition? You will say that B1 cos kx must be equal to C1 e to the power of minus kappa x when x is equal to the, when x is at the boundary. That means, I have to put x is equal to a. So, therefore, I will put a here and I will put a there. Not only that, the derivative of the function should be continuous. So, what is the derivative of this function? The derivative of that function is minus b1 k sin kx, but you have to evaluate this derivative at a, at x is equal to a. So, derivative at that point is going to have an a inside it. Right, instead of x you will have to put a. And then what is the derivative of this function? The derivative is actually minus kappa C1 e to the power of minus kappa x, but you then have to put x is equal to a. So, you are going to get a here and these two have to be equal. And just as we did in the last day's lecture, actually we can divide this equation by that equation, and what is the result? You will find the result k tan Ka is equal to kappa, right. This is the result that you will find. If you just divided, you see this equation by that equation, which actually means that you divide this by that and you divide that by that. And because these two are equal, because this side is equal to that side, then what will happen? If you took the ratio again, the two have to be equal. And if you look back in your notes, you will find that it is precisely the same equation. If you look into your notes, you will find that it is precisely the same equation that was obtained by applying these conditions at the other boundary. Same equation we obtained when we impose the condition that the wave function and its derivative should be continuous at the other boundary. So, we do not get a new equation, it is just the same equation. And the question now is, how do we solve this equation? And let me tell you how to solve it. Well, let me remind you of the definitions of k and kappa. Kappa was defined to be 2m epsilon by h cross square, correct me if I make a mistake, and k was defined to be 2m, oh well, there is a mistake already, this is kappa square, and k square is 2m v0 minus epsilon divided by h cross square, right. This is from the previous day. Again, what was epsilon? Again, let me remind you, I am imagining that the particle has an energy which is that much, right. It is less, the energy of the particle I am assuming is less than 0, and this height I have taken to be epsilon, so that the energy of the particle is equal to minus epsilon, right. That was the notation. So, obviously, if you added k square and kappa square, what would be the answer? Clearly, the answer is going to be 2m V 0 divided by h cross square. That obviously implies that I can write kappa in terms of k. Kappa must be equal to well, before I do that, let me just multiply throughout by the parameter a which is occurring in the problem. You see, this parameter a actually determines the width, 2a actually is the width of the potential well. So, what I will do is I will just multiply this by a square. So, that I will have kappa a square plus k a square is equal to 2m b 0 a square by h cross square. You may wonder why I did that. Answer is actually very simple. See, this kappa is occurring in the exponent, correct? It is occurring in the exponent, that it is occurring with x. Now, in a physical problem, x has dimensions. What is the dimension of x? Length, right? X has the dimension of length. So, therefore, what happens is that kappa has dimensions of length inverse, because if kappa x is occurring in the exponent, anything that occurs in the exponent has to be dimensionless. So, this implies that kappa has dimensions of inverse of length, and so if I multiply it by something which has dimensions of length, the result that I get will be dimensionless, and we always prefer to work with dimensionless things. So, that is the reason why I have taken kappa into a. Why? Because kappa into a is going to be dimensionless, and obviously k into a will also be dimensionless, and this right hand side, this whole thing itself will be dimensionless. It is always nicer to work with dimensionless things. And so, let me say that this entire thing I will denote by the symbol zeta square. I mean, this is simply because I do not want to be writing that whole thing again and again and again. So, I just write zeta square instead of that. So, that means actually I can write kappa into a as zeta square minus k a the whole square with a square root sign. So, there is a relationship between kappa and k, and that relationship I am writing in this fashion, that is all. And now, I know that this equation is to be satisfied, and I have also mentioned to you yesterday that kappa and k are both dependent upon epsilon. Kappa and k are both dependent upon epsilon. So, this is an equation that will actually determine epsilon, which means that this is the equation that will determine the energy of the system. So, I want to solve this equation, and that is why I am doing these manipulations. So, in this equation I can make a slight rearrangement and say that tan k a is equal to kappa divided by k, or I can add an a to both numerator and denominator and write this as kappa a divided by k a, right. I have not modified anything, and then I can say, okay, kappa a is what? Kappa a is given by this expression. So, I could write this as zeta square minus k a the whole square divided by k a. Now, it does look a little bit complex, but what is the answer that I get? I get the answer that tan K A has to be equal to that. So, this is a condition. See, this condition has to be obeyed, it has to be obeyed to have an acceptable state of the system. But look at K, what is K? K is related to the energy of the particle, right. The energy of the particle is minus epsilon. So, only K which satisfies this condition are allowed, and that implies that only those values of E which correspond to that K are allowed. Only those values of E which satisfy, right, only those values of E which lead to a K which satisfy this equation are the ones which are allowed. So, therefore, what should I do? I have to find K in such a fashion that this equation is obeyed, and once I get that value of K, what will I do? I will put that value of K here and evaluate the energy of the system. So, this is the procedure, and unfortunately, you see this equation is a little bit complex, but we can actually find solutions in a fairly simple fashion. We cannot find analytic solutions, unfortunately. So, we have to resort to what is referred to as a graphical procedure for solving this equation. So, how do you solve this equation? And this again is a very interesting thing. See, you have on the left hand side you have a function, on the right hand side you have a function. Both are functions of K, and I want to find the solution. So, how will I do that? The answer is I will make a plot of the left hand side, right, against K. I will also make a plot of the right hand side against K. Let us see what the results are. So, the left hand side I will draw with some color. Okay, the left hand side is tan K A. So, the horizontal axis is going to be taken to be K A. So, the variable now is K A, and I want to plot tan K A in the vertical direction. I hope you remember how a plot of tan x against x would look like, at least roughly. So, the way it would look like is, we see when x is equal to 0, tan x actually is 0. So, it will start at 0, right, it would start at 0 like that, and as you increase the value of x, it will actually increase. But when x is equal to pi by 2, right, tan x, well, instead of K A I am just saying x. So, tan x when x is equal to pi by 2, what is its value? It is infinitely large. So, therefore, the plot would look like this. I have to be a little bit careful. This is the point, x is equal to pi by 2. Correct. But what about the plot beyond this point? Well, it is interesting that the plot starts at minus infinity, something like that, and then it goes to 0 here, and then it goes to plus infinity again, and that will happen, this next infinity will happen when x is equal to 3 pi by 2. And again the plot will continue, and you will have another infinity at what value would you say? The next infinity will happen when the value of x is, or when K A is 5 pi by 2. I mean, I will draw one more. This goes on repeating because you see tan, of course it is composed of sine and cosine which are periodic. So, tan also will be periodic. Correct. And not only that, these points, what is this point? It is actually pi. This is pi and this point will be 2 pi, this will be 3 pi and so on. So, that is the appearance. You see the green curve is the appearance of the function tan. Now, what would be the appearance of the right hand side if I made a plot of it? This function, what is the function? You have a constant. I mean, if you want to get an idea, I can say this is something like, this is a constant. So, maybe I will say 4, this is the variable x, let me say, so 4 minus x square, it is of this form 4 minus x square divided by x with the square root on top. This is the kind of function that you have to think of plotting. Obviously, you see the function is imaginary if x is greater than 2, right. So, we will worry only about the region where x is less than 2. Okay. So, and further when x is close to 0, what will happen to this function? It is going to be infinitely large. So, as a result, what will happen is that when I am going to make the plot here, when you are very close to the origin, the value of the function is very large. So, it starts at infinity, then as you go on increasing the value of x, what will happen? This function will actually, if you think about it, you would realize that it will decrease. So, if it decreases, what will happen? It will go on decreasing something like that, and then what will happen is that finally when k into a is equal to zeta, the function will become 0, and beyond that the function is imaginary, correct. So, therefore, this is the point where k into a is equal to zeta, right. So, this is how the plot of the second function is. The first function is shown with the green curve, the second function is shown with the brown curve. And where is it that the first function is equal to the second function? See, after all, you want to solve this equation, you have made a plot of this function, you have made a plot of this function, and you now ask where is it that the first function is equal to the second function, and the answer is that the two are equal at points where the two curves intersect, right. Those are the points, that you want. So, where are the two curves intersecting? I did have yellow color somewhere. Okay, this is point number 1 and that is point number 2. So, how many solutions would I have if this is the way the two curves were? The answer is that there are only two values of k. The first value is given by this point, which actually means this corresponds to a k value which is somewhere here. This is the corresponding k value. And the second point is there and the corresponding k value is somewhere here, and what should I do now? I have to find these two values of k, put those two values of k into this equation and find out the corresponding values of epsilon, and therefore, there are two allowed energy levels and there is nothing more, only two allowed energy levels, because you see there are only 2 points where the two curves intersect. Okay. I think I will stop and then continue in the next lecture. Thank you for listening.